Hello guys, welcome to my YouTube channel Net Physics by Tanya. In today's lecture of nuclear physics, we will study nuclear spin and angular momentum. Now, the nucleus is basically a collection of two kinds of particles that are protons and neutrons. And they are the kind of particles which have spin half. That means they have their intrinsic spin angular momentum of their own. So you can think that nucleus is a collection of smaller nuclear particles which have their own intrinsic spin angular momentum. Also, in some nuclear models like the shell model, the nucleus is assumed to have a central potential field. That's the shell model diagram basically, but we will study the shell model in some other lecture in detail. Just you can see the diagram here that this is the shell model diagram. So, in such a central potential, the solution of Schrödinger equation will lead to quantum numbers such as the azimuthal quantum numbers, thus leading to orbital angular momentum for these particles. Thus, the nucleus is composed of particles that not only have spin angular momentum but also orbital angular momentum. This contributes towards the spin angular momentum of the nucleus as a whole. The nucleus is then behaves as a singular particle with its own spin angular momentum that has a certain magnitude as well as direction that is quantized by similar rules. So, whether there is an even or odd number of protons or neutrons, that also plays a role in determining what is nuclear spin. Since such particles tends to pair up with each other and cancels each other's spin. So here spin angular momentum is given by capital L plus vector plus capital S vector. Here this L represents the orbital angular momentum of constituent particles, whereas this S vector represents the spin angular momentum of constituent particles. Now this summation Li represents the individual angular momentum of all particles, whereas summation Si represents the summation of all the spin angular momenta of all the particles here. So in quantum system, angular momentum is a kind of physical quantity which experiences quantization not only with respect to its magnitude but also with respect to its direction. So the nucleus behaves like singular particle just like neutrons, protons or electrons. So here magnitude of total spin angular momentum is given by this under root of I into I plus 1 h cut, where I is basically a quantum number and I varies from like 0, 1 by 2, 1, 3 by 2 or sometimes referred as nuclear spin. Also, the direction in which angular momentum is oriented in space is also quantized, and z component of angular momentum in z direction is given by Iz equals to capital M h cross, where this capital M varies from minus I to plus I. For example, if I is equals to 3 by 2 means if nuclear spin is given that 3 by 2, then M will have 4 values: minus 3 by 2, minus 1 by 2, 1 by 2 and 3 by 2. Z component of angular momentum along Z axis can also have 4 different values. The way this can be visualized or the way this kind of motion is represented in 3D space is given by this diagram. So here you can see that this is the z component of angular momentum along the z direction. Basically, if the nucleus is rotating or it has a certain kind of spin in a given direction, then angular momenta is oriented in a certain direction in space such that a z component is any of these values, like here 3 by 2 h cross, 1 by 2 h cross, minus 1 by 2 h cross and minus 3 by 2 h cross. Like here you can see that in case of 3 by 2 h cross, the nucleus is basically precising around a particular conical section like this. Here, like this, it will precise along the given z direction. Similarly, for minus 3 by 2 h cross, you can see that it will also precise for a given z direction like this. In all the four cases, the total magnitude of angular momentum is same, and it is only the z component of angular momentum which is quantized according to m/h cut. Now here we will have different cases like even nuclei. The next case will be even odd nuclei and odd nuclei. So firstly here we are discussing about even nuclei. For example, 2He4, like this is helium atom, this is carbon atom. So generally it is seen that even number of proton will pair up with even number of proton, and even number of neutrons will pair up with even number of neutrons, and ends up like this way in opposite spins, and ends up cancelling each other's spin and orbital angular momentum. Like here in case of protons you can see like opposite spin, and in case of neutrons opposite spin, and they will cancel out each other's spin as well as the angular momentum. So this effect is known as the pairing effect. Here they are cancelling each other in pairs of opposite spin. So here the nuclear spin will have the value 0, and total nuclear angular momentum will also have a 0 value. Now further, that is even odd nuclei. So here I have taken these examples of even odd nuclei, that is 0n1, 1h1 means hydrogen atom, that is helium, and that is nitrogen. But we have taken the case of even odd nuclei here. So here even number of protons pair up with odd number of neutrons because it's the even odd nuclei, and odd number of protons will pair up with even number of neutrons. They try to pair up with each other like in this manner, or cancel each other's spin or orbital angular momentum like the previous one, thereby leaving one unpaired either proton or neutron. That particular unpaired neutron or maybe proton will contribute towards the spin of the entire nuclear system, and that will give the value I is equals to 1 by 2. That means our nuclear spin will have value half, because here it's leaving one unpaired either proton or neutron, so that will contribute. So our next case is odd nuclei. So here we have taken the example of nitrogen and hydrogen. So in case of odd nuclei, odd number of protons pair with odd number of neutrons and cancelling each other's spin as well as the orbital angular momentum. But here in this case there is an unpaired neutron and proton also represents in this case, which therefore contributes towards the nucleus. So it will give the value of nuclear spin 1. So that's about the odd. Thanks for watching. Stay tuned for some more videos. Like, share and subscribe my channel. Bye, Tanya.